Hi, I'm Lorenzo Dazzi from Mälardalen University in Västerås, Sweden. In this video, I'm going to demonstrate to you how Benji, a framework for the systematic generation of model comparison benchmarks, can be used to generate domain-specific benchmarks and evaluate existing model comparison algorithm. But first, let me give you an introduction of the overall architecture of the framework. So given a set of differences and an initial model inside of benchmark specifications, users generate models resulting from the application of the first on the latter. Differences consist of preconditions, actions, and postconditions expressed using a dedicated specification language. The generator converts benchmark specifications to design space exploration problems and produces the final solutions along with a model-based description of their differences with respect to the initial model. In this demonstration, we use Benji to implement the model matching challenge proposed in the literature. In this, past experience from the industrial adoption of model comparison technologies has been used to define a set of 5 differences known to be problematic for most model comparison tools, namely move element, rename element, move renamed element, exchange location of elements, and update target of reference flow elements. So let's dive into the code now. So as you can see, we have defined 2 different projects for the 2 different meta models involved in this model matching challenge. The benchmark specifications are contained inside the main.extend file, whereas the differences have been defined inside the differences.extend file, and finally, preconditions and postconditions have been defined inside the queries.viatra query language file. So as we can see, the demonstration consists in 2 phases. First, we generate models with Benji, and then we execute EMF compare over the generated models, and we compare its results with those generated by Benji in order to understand how well EMF compare is able to detect the given differences. So the first step in generating the models with Benji, we have defined 3 different benchmark specifications for each of the input models expected in the model matching challenge. So for the first input model, what we expect to apply is a move element or a rename element or a move renamed element difference. So we are expecting to generate 3 different models containing these differences. On the second input model, we only want to apply an exchange location of elements difference. Finally, on a third input model, we want to apply an update reference target difference. So let's see now an example of how to define these differences using the different specification language provided in Benji. So we have defined the different specification language as an embedded domain-specific language. More specifically, we have combined the Viatra query language together with the extend programming language. Every difference consists of a name, a precondition, which is defined using Viatra, an action, and a postcondition, which again is defined using Viatra. So in case of the move element, we can see that the move element precondition selects a process or start event, a task, an end event, and 2 different sequence flows connecting these elements. As you can see, the precondition is defined in terms of traces, which are used throughout the generation process to represent an initial version and a current version of a given model element. So in this case, we are selecting a start event. We are interested in a start event that's preserved among the initial version of the model and the current version of the model. We are also selecting a task. Again, we're interested in having a preserved task, so a task that has an initial and a current version in the generation process. And more specifically, we also want to impose that this task has the name being equal to deliver goods, and this name is the same in the initial and in the current version. Then we select an end event and the 2 different sequence flows, more specifically the start event to task sequence flow, which connects the start event to the task in both versions, in the initial model and in the current model. The same applies to the task to end event, which instead connects the task to the end event. And finally, we want to impose that all these elements are contained inside a process, which again is preserved. So the precondition imposes that we have a process containing a start event, a task, an end event, which are connected using flow events. And this precondition corresponds to the first input model of the first benchmark specification, where we can see that we have a process underscore one, a start event, end event, task, and two different sequence flow connecting these elements. So once we have this precondition met during the exploration process, what we want to do, we want to create a subprocess instance, which is a meta class of our BPMN2 meta model. We set the name of this subprocess to send order, and we move all the elements that were previously contained inside the process. We move these elements into the subprocess, and then we insert the subprocess itself inside the initial process. Finally, once modified the model, the post condition is meant to verify that the expected changes have been applied in the models and are used throughout the exploration to understand whether or not a given difference is visible. So in this case, for the move element post condition, we can see that the Viatra query is more or less the same as the precondition. The only difference can be noticed in the last part of the query. So we can see that we have a sub process that was not in the initial model, but is now present in the current model. So this is how we can represent created model elements. And then we go on imposing. We have this sub process with the send order name, and its flow elements contained all the current start event, current task, current end event, and the current flow elements. And similarly, we want to impose that as concerned the process, it only contains these elements in the initial version of the model, whereas the current version of the model does not meet these requirements anymore. All the other differences can be defined in a similar way, as we can see, for example, the rename element difference. In this case, the difference is much simpler. We just select a task. We want an existing task that has a name deliver goods. What we do is that we update the name to send items, and then we just verify that there is a task in the model that used to have a deliver goods name and now has a send items name. Okay, so now once we have defined the differences and our benchmark specifications, what we want to do is that we want to generate the models. And once generated the models, we are going to evaluate the performance of EMF compare by simply taking all the generated input models, combining them with the corresponding generated output model, and then simply running the EMF compare algorithm over them using a comparison scope containing the input and the output model resource. Once compared this model with EMF compare, we are going to get back a comparison, which is an EMF compare specific notation that can be used to represent differences. In order to be able to compare the EMF compare results with our with the Benji with the models generated with Benji, though, we need to have it would be preferable to have a same notation. So what we do in a similar way as done in Benji during the generation process is that we attach a change recorder, an EMF edit change recorder to the input model, and then we use EMF compare to merge the input model with respect to the comparison. as you can see in line 74. Once merged the model, we just stop the change recorder, we obtain a change description, which is going to be on the same level as the one generated by Benji, but containing all the set of changes applied to the model according to what EMF compare has been able to detect, which might be wrong or might be correct. Okay, so you can see we have the folder inputs. Right now we have a benchmark folder that only contains the inputs. We run our okay, as you can see, the exploration process starts, and then the comparison is used to generate the model. So now we can just refresh our benchmark folder, and we're going to have an output folder. So in this case, we were expecting to have 5 different models. As you can see, we have 5 different folders with randomly generated resource ID, and each folder corresponds to a solution of the exploration process. So if we open up, for example, this third case, we can see that this is the case where the rename element difference has been applied. So from the properties, we can see that the deliver goods task has been renamed to send items. The output model, as expected, will contain a send item task instead of a deliver goods task. And in this case, we can see that EMF compare has been able to correctly detect the applied difference. It's interesting to notice that if we open up the eCore model, in this case the models have already been generated, the process is exactly the same. However, in this case, the same difference, rename element, which is supposed to be applied on 2 different elements. In this case, we have an input model containing a domestic animal meta class and a nickname attribute, and the rename element consists in renaming the domestic animal class into pet and the nickname attribute into moniker. So the expected delta model that we want is exactly to have this domestic animal class to be renamed, as well as the nickname attribute to be renamed. However, unfortunately, we can see that EMF compare is not able to detect this difference, but rather it describes the difference in terms of insertion and deletion. More specifically, according to EMF compare, we have a new pet meta class with a moniker attribute, and this in this pet meta class we also add a species attribute, which is moved from the domestic animal class into the pet class, and the previously container package, we can see that we in this case we remove the deleted domestic animal meta class, and we add the new pet meta class, and finally the nickname attribute is just removed as well. So we can see that EMF compare is not able to detect the semantic relatedness that exists between domestic animal and pet, and between nickname and moniker. So yeah, this is the end of the demonstration. We have showed how to generate models with Benji. We have showed how differences can be defined. And also we have shown how an existing model comparison tool can be evaluated using our framework. I think it's interesting to notice that in this case we have selected EMF compare. However, the evaluation process does not depend heavily on EMF compare. More specifically, as you can see from the evaluation code, The only requirement that we impose in order to use this procedure is to have a model comparison tool that generates executable different specifications, or also known as model patches. The reason behind this requirement is that we need to be able to attach a change recorder to the input model source and apply some of the detected changes on the input model in order to obtain a change description that is at the same level of the one generated by Benji. Okay, so thank you very much for your attention. The full source code of both examples is available on GitHub, as well as the core source code of the Benji framework. Thank you again. Bye.